Welcome back. In this video, we're going to explore how we understand the acceleration or the relative acceleration of two bodies when one of those bodies is rotating. Specifically, when we look at how to measure accelerations and velocities from an object from the body that is rotating itself. So in this particular example, again, we're going to have a fixed or absolute reference frame, and we're going to have a rotating reference frame that is on one of the bodies that we care about. This body is experiencing both angular velocity in general and angular acceleration, and object B has some of its own velocities and accelerations. So our objective then is going to find out what is the acceleration of B given that we know everything about A. So if we are on a platform and we want to know relative to us, how is that object moving, we'll need to be able to do the relative acceleration equations. So recall when we were dealing with objects that weren't rotating, we had the relative acceleration equation as the acceleration of B as a vector is equivalent to the acceleration of A plus the acceleration of B from A's perspective. That's still true. So that's dealing like A is accelerating and B is accelerating, and we can figure out how much B is accelerating. If we know both A's acceleration and the difference between those two, we can do the step upwise. Now all we need to do is add the rotational impact stuff from A's perspective. So we just need to add to this A's rotation. So the impact of the rotational frame at A. So as always, we can start with the relative velocity equation. So the velocity of B equals the velocity of A plus the velocity of B given A from A's xy frame. And then we need to add the rotational component. So plus the rotational component of A crossed with the distance between B and A. So if that's our relative velocity equation, we can take a time derivative of this, and we should come up with the relative acceleration equation. So notice that there's going to be some chain rule going on because we've got a multiplication going here. So the acceleration of B, the derivative of the velocity, of course, is just the acceleration of B, has to be equal. Derivative of the velocity of A is the acceleration of A. That part doesn't change. But what does change is we've got, let's go ahead and deal with this part first. We're going to have the derivative, the time derivative of the angular velocity, A, crossed with RBA, and the other side of that, right? So we've got to do the angular velocity of A crossed with that time derivative of RBA. And then lastly, we have to have the time derivative of the velocity of B given A's reference frame. And notice that this time derivative is also going to have a component of how much the angle is changing, how much the angular velocity is changing. So there's several different parts to this, and what ends up happening is we can treat them by parts. So if this little bit here is our first part, and this little bit here is our second, and this little bit here is our third, let's kind of break this out into parts because this ends up being a pretty long equation. So first of all, this is probably the easiest portion, is that we've got the time derivative of angular velocity. Well, that's what we call angular acceleration. So that's the angular acceleration crossed with the r vector. Number two is that we have the angular velocity crossed with the r vector. So the angular velocity of A crossed with are b given a plus the velocity of b with respect to a. And then finally, we have the time derivative, or the angular velocity, excuse me, of a crossed with the velocity of b given a, and the acceleration, the time derivative of the BA, which is the acceleration of B from A's perspective. All right, so that's a whole lot, and there's a couple different parts that repeat. So there's a cross product here and a cross product here that does the same thing. So we end up with one equation that is the thing that you write down and you'll use, is the acceleration of B, the linear acceleration as a vector, is equivalent to the acceleration of A plus the angular acceleration of A crossed with that r vector. And of course, these are all vectors. And then we have a angular velocity times a linear velocity, and the linear velocity is just angular velocity times the radius. So there's two angular velocities in there, and when we do that cross product twice, we end up with a negative. So that would be saying plus the angular acceleration of A crossed with the angular acceleration of A crossed with that RBA. That gets us to this far, plus these two components, so the angular velocity twice, plus 2 times the angular velocity of A crossed with the velocity of B given A. Make sure we get all of our vectors on here. And then the last part, adding to all that, is that last little bit, the acceleration of B from A's perspective. All right, so let's think about this in parts. So first of all, the acceleration of B with respect to A, we've got to at least start with the acceleration of A. Once we have that as our platform, then what we'd need to do is add these two components. And what these two components are is, let's pretend for a moment that A is fixed, and we're back to what we've talked about before in kinematics, is that we know the acceleration of B, given that we've got some fixed rotating link here, and some angular velocity and angular acceleration, we know the relationship between those things. So the tangential component is alpha r, and it acts tangentially. So that's alpha r, and it's acting tangentially. You'll get your direction based on whether it's positive k or negative k. And then next is a angular velocity times an angular velocity. That is angular velocity squared r, and it's going to be acting down in the r direction. So cross product times a cross product, we end up with minus angular velocity squared times r in that r direction. Then the next portion is this kind of something I'll save off for a second. It's this 2 times the angular velocity crossed with the velocity, which seems like a kind of a weird quantity. And then our relative angular acceleration. So that is, if we had a sensor on A and we were looking at B, how fast does B appear to be accelerating away from A from A's perspective? So that's generally something we want to find. So the thing that is kind of new here is this quantity, the 2 times the angular velocity times the linear velocity from A's perspective. So this portion here, this 2 times the angular velocity crossed with the linear velocity from A's moving perspective, this is the Coriolis component. Or what's known as the Coriolis effect. So when you are in a rotating reference frame, objects appear to accelerate or have a curvature. And that curvature is really only explainable by the fact that there's another component in our acceleration term, and that component is 2 times that velocity. So in things like being on the planet Earth, we can observe if you had a really good like gun or something that can shoot really far, there's some curvature effects that end up happening because the Earth is actually rotating faster, and your bullet will go one direction or the other. And that's a Coriolis component of that velocity. Of course, it only happens on really big time scales when you're talking about such huge, massive objects. But you can see this even in simple examples. If you go to a playground and you got one of those rotating rings and you throw a ball and you try to throw it to a person who's also on that rotating frame, they'll miss it because from a fixed perspective, of course, that ball is going to go straight. But you're in a rotating reference frame, so as that ball is coming towards you, you move out of the way. So to explain that movement of the ball from the rotating person's perspective, it appears that it misses you, it moves out of the way. Although from a fixed perspective, you won't see that at all. So that ends up being the Coriolis component of acceleration, and it explains why if you're on the Earth and you see hurricanes or typhoons forming, that difference is caused by this Coriolis effect where things appear to spin or from this rotating reference frame.